So I'm back with yet another vodcast, pretty short, about a special kind of galvanic or voltaic cell called a concentration cell. And what's so weird about these cells is that the two half cells are identical in terms of they have the same metal anode or same metal electrode, in this case nickel, and they have the same ions in solution, in this case green ions of nickel 2+. But what's different about these is that you can see that the concentration on the left-hand side is fairly small, 0.001 or 10 to the minus 3 molar, and the concentration on the right-hand side is 1 molar. So what happens is that the electrons will spontaneously flow from the anode to the cathode until the two concentrations in the half cells become equal. When that happens, the electrons cease to flow and the cell is dead. Notice it has a 0 voltage when the cell is dead, and a very tiny voltage, but still a voltage nonetheless of 0.0888 volts. So what's very interesting about this is you see time go by. This is the before picture, this is the after. Notice that the more concentrated half cell, the cathode on the right, becomes less concentrated. The dark green comes from nickel ions. So nickel ions must be disappearing over here at the cathode, and they're not really disappearing, they're being reduced. As electrons come down the pike, this half cell, the green nickel ions pick up electrons and plate out on the electrode as nickel atoms. So that's why the concentration of the nickel ions on the right, originally more concentrated, became more dilute. On the left-hand side, we start with 1 times 10 to the minus 3 molar, and we increase in concentration to 0.5 molar. Well, that makes sense because as we have nickel atoms lose electrons that pass through the external circuit, nickel ions flow into this originally more dilute solution, and the picture doesn't show it very well, but this should have been a little bit shade of darker. So this is a weird thing called a concentration cell. Now, I did best I could on getting some text out of the textbook to help explain this, and you can look at it again yourself. But when you look at a cell like this, the standard voltage would be 0, because you would go cathode minus anode. It's the same reduction half reaction, and if you go cathode minus anode, you end up having a positive added to a negative, and you get 0 under standard conditions. But these are not standard conditions. Because the concentrations are different, our Q is not 0. Remember our reaction quotient? And as long as the concentrations are different, the electrons will flow and the voltage will not be 0. Now let's take a look at this best I could do screenshot of what you can see in the textbook. At the anode, solid nickel atoms come off the electrode and turn into nickel ions, and we're going to call that that's the dilute side, just to keep it straight, and the 2 electrons go through the external circuit. Over at the cathode, the 2 electrons flow over and attach themselves to a nickel ion that started out fairly concentrated, and nickel solid gets plated out at the cathode. So the net result, if you sum these 2 equations together and cancel the nickel solids and cancel the 2 electrons, is nickel ions over on the concentrated side yield nickel ions that are more dilute. So the only reason we've set this up is so we can calculate a Q. Remember, we'll have product concentration divided by reactant concentration. So let's take a look how you'd solve this. I cut off on the far left, the non-standard voltage. So pretend that there's an E over there. And the Nernst equation says if you have the standard voltage minus 0.0592 over the number of electrons flowing times the log of Q, you can get the voltage under non-standard conditions. So what's missing over here is just a plain old E. Well, we know that the standard voltage has to be 0 because the 2 reactions are identical and yet opposite to each other. And the Q would be the dilute ions, and that's why they're here over on the right as a product concentration, divided by the concentrated nickel ions concentration over on the left-hand side. And that was given to you. The dilute half cell started out as 0.001, makes our math easy. The molarity on the concentrated cathodic half cell is 1. So by the time you get done crunching these numbers, that's where that tiny voltage of 0.0888 came from. So concentration cells are really kind of weird because the only reason they flow is because of a change in difference in concentration. Notice that if you ever had these two concentrations equal to each other, you would have the log of 1. Well, the log of 1 is 0, and 0 minus 0, because this whole expression here would become 0, because 0 times 0.0592 over 2 is also 0. That would still give me 0 volts. So when the two concentrations are different, electrons flow a voltage registers. When the two concentrations are the same, your Q will be equal to 1, which is the log of Q equals 0, and 0 minus 0 is 0. So the cell would become dead and electrons don't flow. Now there's a very different kind of problem that you can see on sample exercise 20.13. And this time they have kind of a hydrogen gas and hydrogen ion type electrodes at both the anode and the cathode. So it says electrode 1 has standard pressure, 1 atmosphere, but we don't know what the concentration of hydrogen ions are. Over at electrode number 2 is one of those sheaves where the hydrogen ion is 1 molar and the pressure of the gas over the cell is 1 molar. It's standard temp, and someone actually hooks these two guys up and reads the voltage as 0.211. Here's your hint. The electrical current flows from 1 to 2. So which one is the anode? Think about it. You're correct. We've got to have electrode number 1 must be the anode because the electrons always flow from the anode to the cathode. Now they want us to calculate what the hydrogen ions are over at electrode number 1. And from that, you could take the negative log of the hydrogen ions, as we learned last year, to find its pH. So, first step is, let's pull up the Nernst equation. We're still in non-standard conditions. This is the voltage that somebody measured. Because the two half cells, as you show down here, are exactly the opposite from each other, and because the reduction potential of the She is 0, then the reverse reaction would also be 0. So that's where this 0 standard voltage comes from, just like the previous problem with the nickel. Here's our little constant combination, 0.0592, and the number of electrons that must be flowing, because it's H2, a Brinkelhoff diatomic element. That means hydrogen ions have to pick up 2 electrons to be reduced and turn into hydrogen gas that you would see come bubbling off at the other electrode, number 2. So let's see what else we've got to figure out here. Oh, we need the log of Q. So we rearrange this equation to solve for the log of Q, and that's basically all the numbers that we punched in, and we get a negative 7.13. So if that's the log of Q equals negative 7.13, then take 10 to the negative 7.13 to equal the Q. So hopefully so far, what we're finding out is what's the pH, but first we have to find the reaction quotient. Then we'll have to find hydrogen ion concentrations, and then we're going to have to find pH. Let's keep the picture of those 2 electrodes in our mind if at all possible. Don't think they're on the next slide. Yeah, they're not. So I'm going to go back because you're going like, huh? Where'd all this stuff come from? But let's go back and take, it's kind of like that nickel ion concentrated nickel ion dilute in the previous problem. Pretend that you took these 2 equations and added them together. Electrons would cancel, and over on the right-hand side, you'd have hydrogen ions from electrode 1 and hydrogen gas from electrode 2 on the right-hand side. Those would be your 2 products. So next slide, that's why there's hydrogen ions squared and the pressure of hydrogen gas at electrode 2. Those were the 2 products that were on the uncombined equation over here. And on the left-hand side, you'd have hydrogen ions from electrode 2 and the pressure of hydrogen gas at electrode 1 left when you sum those 2 equations. So that's why On the left-hand side, which equates to the reactants, remember it's products over reactants, we have hydrogen ions from electrode 2 squared, because there was a 2 in front of them, times the pressure of hydrogen gas at electrode 1. Well, if you travel back to see what they gave you, the thing that was missing is the hydrogen ion concentration at the first electrode, at the anode. The hydrogen gas pressure was given to you at the electrode number 2 as 1, because that was that She, the standard pressure is always 1. The hydrogen concentration of ions at electrode number 2 was also 1 molar, and supplied in the problem was the partial pressure of hydrogen gas over at electrode number 1. I think I've got all those straight. Well, here's a whole bunch of 1s. Well, I love this problem, because all those 1s go away. And we get x squared is equal to q, and the q that was previously solved was 7.4 times 10 to the minus 8. We're searching for x though, so I have to take the square root of 7.4 times 10 to the minus 8, and lo and behold, there my calculator is 2.7 times 10 to the negative 4. That is the concentration of a hydrogen ion. Deep breath, not done. The pH is always found by taking the negative log of the hydrogen ion, so we can turn it into a positive number that can fit on our 0 to 14 pH scale. Here they are doing that, and we come up with a pH of 3.57. And of course, it's going to have to be less than 7 because the pH has to be acidic. So I think that's it. Kind of strange problems, these concentration cells. The last topic of the chapter that we'll be dealing with has to do with electrolysis, and in your PowerPoint notes you were given a reading assignment over the weekend. I will not be covering things like batteries and direct applications of cathodic and anodic reduction and potential reduction and oxidation reactions. So do that reading assignment, not too much emphasis on that material in the next 2 sections, and I'll meet you again when we talk about electrolysis.